o senhor Mike vai ministrar a seguinte palestra: sistemas de cobertura de pilha e barragens para minimizar a contaminação de água. Então, vou passar a palavra para o senhor Mike Milczarek.
Thank you, Flavio. Can you please share or make me the host? Okay, can you see the screen?
Yes.
Okay, perfect. So today I'm going to provide an overview discussion of closure cover systems to reduce infiltration into waste rock and tailings and hence minimize acid rock drainage. I won't be providing any specific details as to how to design cover systems, how to characterize materials. I'll be giving a workshop with Flavio at the next acid mine drainage conference in October, and we'll be providing much more detail at this time. But so this is just kind of a very broad overview of what things are important and what things to consider as you design for closure cover systems. So there's obviously a lot of challenges at different mine site, and each mine site's different and has its own challenges. And the issue is the ingress of oxygen, water, and waste in the rock that was formerly under reducing conditions is now in oxidizing conditions, and it may start to, depending upon whether it's mineralized with sulfides, it may start to generate acid mine drainage. For closure, this obviously creates difficulties because you need to avoid the release of any acid mine drainage into surface water or groundwater systems. It also creates problems with mine waste and inability to revegetate. Specifically, if the pH starts to drop below about 4.5, you start to get the solubilization of metals like aluminum that are quite phytotoxic. And then finally, the surface needs to be stable, and we need to be able to control surface water and control erosion from the cover system. So that's the main topics of my discussion today. So in terms of covered system, the first goal we have is to control the net infiltration, keep water out of the waste. We also want to revegetate it if possible, especially this depends on the post-mine land use, especially if there's any type of wildlife habitat or livestock grazing that's planned. We need to be able to get things to grow and be healthy in the cover system. We want to control the surface water runoff, long-term erosion control. And these are just some pictures of some sites where we've worked at in different parts of the United States, in Peru and Papua, where we have successfully reclaimed different mine sites. And I'll be talking about a few of those as we go on. So what are the controlling factors? The major controlling factor, obviously, is the climate. In arid and semi-arid systems, it's much easier to keep water out of the waste. The cover system designs can be quite much more simple. It's also a function of the mine waste characteristics. Waste rock is quite different from heap leach. Well, it's different from tailings material for sure. And heap leach, depending on whether it's crushed or run a mine, can behave quite differently. And these affect the design, both in the case that if you use a ET cover system, it becomes part of the cover system and affects the performance, as well as for the design, tailings experience variable consolidation. I'll be talking about this, but you have to have different considerations and possibly different designs for different materials. The cover material properties are quite important, and this depends on what type of materials you have on site, what you're available to borrow. This will affect your net infiltration rates. Finer grain materials are better at holding water for vegetation to use, and therefore you can get lower net infiltration if you have fine grain soils on site. However, you don't want to be putting fine grain soils necessarily on your side slopes because that can affect your erosion rates, and I'll talk about that. And then, of course, are you able to revegetate these materials with native species preferably? So ultimately, you have to design for the site conditions because the climate affects your design, and the borrow materials you have on site will affect what you're able to do in terms of the cover system performance. So I want to talk briefly about mine waste characteristics. Three major mine waste types. Your tailings are obviously crushed rock. They're put down in a fluvial depositional process. This creates a higher layered system. And typically what we see is that in the areas where the deposition is occurring, whether from spigots or from cyclones, the coarser sand material will drop out. This is the beach, this is the dam material. And so that is fairly high permeable. It doesn't have as high a water holding capacity. As you get farther back into the tailings impoundment towards the decant pond, or what's often called the slimes area, then you get much finer grained material. And this will affect how, if you put an ET cover system on it, how the flow occurs and how water goes into the mine waste. And the other thing to consider with tailings is you will have consolidation and deformation over time as the tailings start to drain. Waste rock has a high percentage of rock and gravel particles. This creates macropores and preferential flow. So there's also a significant storage capacity in the waste rock material. Typically, when waste rock comes out of the mine pit, it's anywhere from 2 to 5% moisture content. That means that it can absorb a lot more water over time before you actually start to get flow out of the bottom of the dump. So this is a consideration, at least in terms of the short term, depending upon the climate, of course. In a wet climate, it may just be a few years before the dump gets wet. In a dry climate, it could be 100 or several hundred years before the dump gets sufficiently wet to actually start getting flow through it. Heap leach material has similar hydraulic properties as waste rock material, but you're already at near saturated conditions. So under this case, if you design a cover system, whatever gets through the cover within a few months will start reporting down to the bottom, because basically you're just pushing water that already is in the heap leach material through the system and out the bottom. So the consideration in terms of water treatment and what the long-term costs are much more rapid with heap leach material. So I won't spend much time talking about geochemical characteristics because there's several talks today that go into detail. But in general, there's in terms of the cover systems, you have two types of waste rocks: your sulfide waste rocks and your non-sulfide waste rock material. And with the non-sulfide material, or material that has high neutralization capacity, it's possible that you could directly revegetate it depending upon the climate. And so these are a consideration, and just getting an understanding of what the acid rock generation is important, because this can also affect the properties. For example, you may have high neutralization capacity, but if you have high acid generation potential, those minerals will start to oxidize, generate acid, and they may be neutralized, but what you have is a very saline system. So in a semi-arid environment, it then becomes very difficult for plants to grow in that material, even though it may be circumneutral and have a high pH. The other things that to consider also is that if you can stay ahead and keep water out of the system before the pH starts to drop below 5, then you're going to be much better off, because once the pH drops below 5 in your waste materials, the acid generation starts to become biologically mediated, and the rates of acid generation goes up by orders of magnitude. So one thing I just want to point out is that there's going to be a lot of discussion about acid-base accounting and static tests. In general, if you're going to consider and you want to keep your material neutral, you want to have a net neutralization potential above 20 tons of calcium carbonate per 1,000 tons, or at least 1.2 ratio neutralization to generation potential of 1.2. In some that we try to keep above 2. Flavio, did you have a question?
No, go ahead.
Okay, there was just background noise. Okay, so This is an example of what kind of a matrix approach you can look at in terms of your geochemistry. So if you have low pH, let's start here. If you have low acid generating material and high pH material, this is fairly low risk, and the waste may be benign. So you may be able to actually directly revegetate this material, and you have a low risk of long-term acid generation potential. As you get on the other end of this spectrum, where you have high acid generation potential, meaning it's going to continue to generate acid and you're already at low pH, this is obviously high risk. You're not going to be able to grow anything in that. And then you need to cover it to avoid surface water runoff and groundwater contamination issues. And so that really drives the cover system design in terms of you need to be thinking about increasing cover system depths and more design complexity. So I'm going to talk briefly about direct reclamation of mine waste. Now, direct reclamation is not that easy because of a number of reasons. Basically, there's typically low plant fertility. There's a lack of organic matter and microbiota. So these are not soils, and it may take quite some time to develop soil properties. As I discussed, they can be saline even if circumneutral. And so generally speaking, to get waste rock or tailings material to revegetate, we need to add some type of organic amendment to boost the organic matter to get the bugs into the tailings so it can start do nutrient cycling. And the other thing to consider is you need to use what we call pioneer species, or species that are used to disturbance. Now, I wanted to talk about this. In semi-arid climates, typically it's and by that I mean less, between 200 and 400 millimeters of precipitation. It becomes quite difficult to do direct revegetation, and usually this is a problem of salinity, because the salinity builds up in the waste and it doesn't get flushed out by precipitation. And so this is an example of some tailings that we revegetated using biosolids as an organic amendment. And even though we were able to revegetate them, there was only 2 or 3 native species that were able to grow. And so the species diversity was quite low. And in the end, it was actually going to be cheaper to use borrow material and put in an ET cover system over this tailings than it was to try to directly revegetate it. Now, in humid climates, it's a different story. This is an example of some revegetation that we're helping Oktedi Mining, which is in Papua New Guinea, to work with. And there they have about 5 meters of rain per year. So this is quite useful, even though their tailings has high acid generation potential, or moderate acid generation potential. There's quite a bit of limestone that's added, and so it's generally circumneutral. And any salinity accumulation is washed out by precipitation. And in this case, Oktedi is right along the border with Irian Jaya, Indonesia, as well as and on the island of Papua. And so the mine is up in the highlands, and then down, they actually directly deposit their tailings into the river. And waste rock, though those designs are changing, and then they dredge the Oktedi River farther down in the lowlands, and then they put it on. They have 2 tailings repositories on either side of the river. Now, this is a quite difficult situation, actually, even though it might seem to be simple with 5 meters of rain, but these tailings are not like the natural system. The natural soils are fairly fine-grained, and there's also very shallow to groundwater. It's typically within 1 meter to 2 meters at the most. These systems may have several meters to groundwater. It's generally coarser material. So it's also higher pH material. So this is a challenge. And some of the things that we've been looking at with them over the years is to add amendments. Do you do seeding, or do you do pole planting? And so there's quite a bit of experimentation that needs to happen to optimize the revegetation methods. And then what we've been focusing on mostly for them lately is the monitoring of their vegetation success. And this is some examples. This is an area where they've been using mostly direct planting. So you can see that there's not much coming in between. These trees will get quite big. In this case, they're using a mixture of direct planting as well as seeding, and you can see that the vegetation success is generally better. And that's where our recommendations at this point is to use both planting and seeding. And this is something that we work on, which is called ecosystem function analysis. It's a way of monitoring vegetation, monitoring soil development, and you can see that from their progress, they're making decent progress. This is the projection of how the progress is going to be over time. And the whole thing about ecosystem function analysis, which is quite a useful tool, is that it allows you to look at the trajectory of the reclamation, and it tells you whether or not it's working or whether or not it's, and you want the diversity of plants to grow up over time. You want the soil to be more stable over time. And it's a nice tool to use for reclamation monitoring. Now I want to talk about climate effects on cover system performance, because that drives the design. So these next few slides are just to show how ET cover systems work. This is an example from a semi-arid environment. Actually, these photos are from a site we worked on in Nevada. And so you have the mine waste below the ET cover system, and this is what we call a monolayer cover system. And this is fairly fine-grained material. And I don't remember, but this was about a meter thick. And so the way ET cover systems work is they store water during the wet season, or the winter in this case, and they store the water, and then it gets used by vegetation later on in the season. So during the dry season, the soil is initially dry. The wet season, you start to get rain and snowmelt that starts to fill the profile, and the soil is holding onto the water. In the later wet season, if you get enough precipitation, the water may actually go through and start going down into the waste. Then during the dry season, you start to get a drying of the upper profile. Vegetation is using it, transpiring the water. And then in late summer, you will have a combination of drainage that's occurring, that's going down, as well as further evapotranspiration. Most monolayer cover systems, even if they're over acid material, there will be water that will come back up over the waste. Generally speaking, if the cover system's thick enough, the amount of water that actually comes up from the waste, it can be quite low, and the cover system will not be affected in the long term. And what you end up with then is a water balance that you can look at the cover design factors. And so you want to have hopefully an ET cover system that will store most of the water on an average year. But in general, it's quite affected by the material properties. Coarse grained soils will not hold much, maybe 2 centimeters per meter. And then you can have 8 centimeters, even as much as 15 centimeters per meter, depending upon the material type. However, like as I mentioned already, the gravelly soils may be better on side slopes than the finer grained soils that will go on the top. Oh, and the last thing I wanted to mention was in semi-arid sites, depending upon the vegetation, trees, for example, the rooting can go several meters deep, and so the ET zone can go several meters deep. And this right here, this break between the arrow going up and the arrow going down, this is often what we call the zero flux plane, or also the maximum, the maximum evapotranspirative depth. So switching to a more humid climate where you have a multi-layer, or what we call barrier layer system, where we have topsoil, we have low permeability clay, silt material, and then a drainage layer. And the function of the drainage layer is to move water away from the barrier layer and get water out of the system before it can leak into the mine waste. And I'll talk a little bit more about that in a minute. So you have precipitation, runoff infiltration, the redistribution, so the water, some of the water will go out of the drainage layer and some of the water will go in, back, continuing to go into the low permeability clay layer. And then ultimately you have evapotranspiration and then net infiltration. In many cases in humid climates, you have a water table down by at the bottom, and whether or not that system's lined is, again, site specific. There may be reactions, evaporation that occurs within the waste that will change the water budget. And then eventually you get either groundwater recharge or discharge to the bottom of the pad. And so these are the components of the water budget that you need to consider for the analysis. Precipitation, what's your runoff, redistribution, as well as evapotranspiration. So I wanted to just give an overview of some of the measurements that have been made on cover systems at different mine sites. And we're starting to collect a fairly good data set, a body of work that shows us how cover systems are working. So in the semi-arid southwestern US, and this is an area that gets anywhere from 200 millimeters to 500 millimeters of annual precipitation, depending upon the location. Elevation is a significant component of that. The higher the elevation, the higher the precipitation. In uncovered waste rock, anywhere from 15 to 40% of the precipitation may go into into net infiltration. With an ET cover over waste rock, we're seeing cover system efficiencies of anywhere of typically 1 to 5% of average annual precipitation. ET cover over tailings is typically better, 1 to 3%, okay? And that's because the tailings will hold up the water, it's finer grained, and it keeps the water from percolating down into the waste as compared to waste rock, which is higher permeability. High elevation Rocky Mountains, USA, this is anywhere from 250 centimeters to 600 centimeters of snow, okay? It can be quite significant. Uncovered waste rock can be greater than 50% of the annual precipitation. And depending upon the covered waste rock on the cover system design, a very simple design still might leak as much as 40% of annual precipitation. Again, it depends on the location and the design. High elevation Andes, typically greater than 3,500 millimeters. They get anywhere from 1,000 to 1,500 millimeters of average annual precipitation. Similar statistics where you have 50% or as much as 50% or greater will go into net infiltration for uncovered waste. Covered waste rock depends on the cover system. It could be anywhere from less than 5% to up to 40% for a pretty simple design, like just a 30 centimeter topsoil design. In Brazil, I'm not aware, there is one site that's being monitored and it's looking quite well. I believe that's in Bahia. And it's generally it's generally drier in that area, but in some of these other zones, we just don't have any data yet. So I wanted to talk about the precipitation, the climatic regions in Brazil. This is a map of the annual average precipitation in Brazil. And you can see up in the area of Bahia and some of these other states, you actually may get less than 700 millimeters precipitation. As you go farther south, the precipitation starts to pick up. And then, of course, as you get into the Amazon, precipitation can be quite high. And then looking at the different vegetation land types as classified chrome. Again, you have tropical zones to temperate zones where it's actually quite, it never gets too hot or too cold down in this area. So in general, what you would expect is that in this area of Brazil, you will probably be able to use a simple ET cover system and then as you get into these other regions where there's more precipitation and overall a lower precipitation to evaporation ratio, at these points, you might need to get into more complicated type cover systems. The other thing I wanted to mention is that the climatic cycles, the Pacific Decadal Oscillation, if you're on the western side of South America, as well as the Atlantic Meridian Oscillation, as well as ENSO, or what's known as La Nina, these significantly affect the climate. And for example, what we have here is these are some data from a gauged watershed that we have. There's a period of time where the record's missing, but this is a fairly large gauge watershed in southeastern Arizona. And we can see that there's distinct periods where you get higher precipitation and higher surface water runoff rates. There's periods of time where there's droughts. This is related, this particular period of time is related to the positive, or what's called the warm PDO. So these climatic cycles need to be considered as well in the design, because, for example, if you design it and you're thinking that this is the climate record during this period of time, or maybe from 2000 to 2020, you're going to underestimate how much precipitation the system is going to receive when the PDOs comes back. Okay, so we have to be looking at climate records over. We like to estimate 100-year climate cycles. So the last thing I want to say about ET cover systems is that they're dynamic. This is a study we did with Barrick at a property that they closed in 1998. And this consisted of a low permeability barrier layer with ET cover. And what we can see here is this is the outflow from their heap leach facilities. There was 3 heap leach pads here. And you can see that during the initial period of time, there was the outflow from the heap leach pads was fairly low. It would coincide, there'd be a several month delay after the winter season and what we call the spring freshet, where they get maximum peak flow. But then sometime in between around 2005, 2006, cover system performance actually went down and it changed. And so what we see over time is that initially the net infiltration control was working as designed. Around 20% of the annual precipitation was coming through the cover system. And over time that has changed. And now there's about 50% more precipitation that's coming through the cover system. And so this is another consideration in terms of the design that you need to think about. Okay, now this is a graph that we looked at when we did this study as well with Barrick, and we looked at what are called precipitation to the potential evapotranspiration ratio. And so this is a study that was done looking at primarily landfills in the United States, which had installed ET cover type systems. And what we see is that there's a distinct pattern of the annual precipitation over potential evapotranspiration that once you start to get above a ratio of about 0.8, at that point, you start to get very high net infiltration rates. Likewise, if you're around 0.4 or you get below 0.4, the annual precipitation rates the annual net percolation rates tend to be quite low. So from this, we can kind of say that you generally have low percolation rates below 0.4. If your P over PET ratio goes above 0.8, you can be expected to have high percolation rates regardless of the ET cover system. Now, this is for North American climates. We need more data for South American climates. So in terms of the cover system design, some initial cover system design considerations, it's going back to the precipitation to PET ratio, is that if you're below 0.4, most likely you can use a very simple ET cover type system. If your precipitation ratio is between 0.4 and 0.8, an ET cover system on your side slopes is probably okay. You might want to consider barrier layers on your flat areas, because typically your flat areas, they don't get much runoff. And so they can be focus points for net infiltration. And so there's some low hanging fruit there where you can reduce net infiltration on your flat areas by going to a more complicated cover system. And then you're also starting to get into the range now where you can consider direct vegetation for non-PAG materials. Once you get above 0.8, at this point, you may want to consider designing barrier layers for PAG material. And again, you have an opportunity to do direct revegetation for non-PAG materials. And then, as I discussed in general, with the thickness and complexity of the cover system, as you go from tailings to waste rock, it gets typically a little bit more complex. So just some examples of barrier layer cover systems. Here's an example, and I already kind of showed this, where we have clay, we have 15 centimeters of a drainage layer, and that's to basically take the water off of the clay. And then you have an organic soil. This would be the same system without the clay layer, but the drainage layer. But what we've seen is that these systems, there's not a huge advantage over just a monolayer cover system, typically, because you have to get water out. So either it goes out the drainage layer, or it goes out a runoff. And so you might actually cause erosion problems if you have very good low permeability clay. Going to a geomembrane type system, again, we have a geomembrane, a drainage layer, and here you absolutely need a drainage layer, especially on the side slopes, because if you don't, you can create saturated conditions and this material will just slide off the geomembrane, especially in the seismic area. Other types of barrier cover systems which have not been used widely in mining yet are but are being used quite a bit in landfill closures, are what's called agri-turf or closure turf. And this is basically just looks like an artificial grass. And this is a landfill that was, I believe, installed in Georgia, which is in the southeastern United States, which gets quite a bit of precipitation. And here you have a geomembrane, and then you have basically your artificial grass that sticks up, and then a sand layer. And you can't, if you look more closely, this is not like an artificial grass that you see at the soccer field. Okay, this is there's not as much grass, and it's a much cheaper installation than artificial grass that you play for football. Now, so the design process basically is a several-step process. And the first, of course, is to identify and characterize your waste and potential borrow materials. You need to get an understanding of what the physical and the hydraulic properties are, the geochemical characteristics, and the ability to support vegetation, looking at soil fertility, nutrient cycling. I won't talk about this. Like I said, we will be giving a workshop in August. And then develop some alternative cover systems. And initially, this is just conceptual to look at what are some options that are available. And then from that, you can develop some estimates of cover system performance, especially looking at net infiltration and erosion control. And then from that, you want to select maybe 2 or 3 designs and then do a trade-off analysis. And that trade-off analysis needs to look at your capital expenditures as well as your operational expenditures between the different cover system designs, as well as long-term maintenance and water treatment. And the water treatment is quite important, because if you have a PAG waste rock facility or PAG tailings, and you have to treat the water, the question becomes, well, what is the, how long am I going to have to treat this water? And then what is the NPV on the water treatment costs? And so this actually is a very important step. This is just an example of some different cover system alternatives. This was from a project that we've been working on in Peru. Very simple. For example, alternative A is a very simple monolayer cover of 30 centimeters of topsoil. And then we start getting some more complicated designs where you have a barrier layer, compacted clay with a drainage layer. We look at some geomembrane. Excuse me, let me go back. we look at some geomembrane options, closure turf. Also, there's some other options, trisoplast, and then they wanted to look at commingling of tailings and waste rock as well. So this is where you start, and then you walk through, and you can kind of tell, at least in terms of just some different costs, getting some unit costs together, what is going to possibly be feasible versus not feasible. Of course, if you are going to go with a clay type system, you have to have clays on site. You don't want to be dragging clays onto your site from 50 kilometers or 100 kilometers away. So in terms of we just went through this. So in terms of the waste and cover material valuation, what we like to do initially is to look at the mine dumping records, what is available in terms of soil and surface geology map. From this, you can often come up with some initial estimates of what the hydraulic properties are. There are things that we call Pareto transfer functions. You can look at like the Kozeny-Karman equation. There's also Mbonimpa that can give you an idea of what the physical properties of these materials might be. And then that will help you with your initial design evaluation in terms of what you want to investigate, and going out and test pitting, drilling stockpiles, for example, and then actually collecting the samples and doing a very good, very careful job in terms of looking at what the materials are, what the physical properties are, hydraulic properties, geochemical. Another thing that we like to do that's quite important is to look at rooting and vegetation in the native soils. So what does the native what do the native vegetation, how big of a rooting depth do they need? Is it 1 meter? Is that adequate, or is it deeper? The only way you can really do this is just to go and dig some test pits and some native material and take a look and do rooting surveys. And that can tell you, also guide you as to what is an appropriate cover system depth that will support the vegetation there. And then out of this, there's a number of models. I won't discuss this. We again refer you to the workshop that you can use to evaluate cover system efficiency as well as erosion. And then from that, you select where you can get your optimum cover material. Now, this is just an example of looking at some different cover system designs. And this is a simple cover, and this is a semi-arid site that gets about 350 millimeters of precipitation a year. And so we looked at different cover system depths that we modeled anywhere from 30 to 90 centimeters. And on the tailings beach and the tailings side slopes, and these are these areas where I was saying that the coarser tailings material, we found that increasing the cover system depth to about 90 centimeters would continue to decrease the net infiltration that would occur through the cover system. Whereas in the slimes, because the tailings were quite low permeability and they would hold the water up into the cover system, the effect of increasing cover above 45 centimeters was not significant. So you can end up with variable design on your facility where one part can have quite a bit more cover than other parts, but you can only do this through a good characterization process and some modeling. This is another example of where we've used modeling, and this is with a barrier layer cover system, and this is looking at what is the effect of the compacted clay layer that's sitting below the drainage layer, and in terms of the efficiency of the cover. And so what we see here is that basically with this, if the permeability of the compacted clay, once it starts to go above about 10 to the minus 6, then at this point you start to lose the efficiency of the cover system. So this is the net percolation on this axis as a percent of precipitation. So if you can stay below 10 to the minus 6 or it get down to 10 to the minus 7, the efficiency is quite high. You can get you can exclude 98% of the precipitation if you have a clay that has 10 to the minus 7. But if you have a clay that's only 10 to the minus 5, it works very poorly, and there's really no difference between just using a topsoil cover system. So these are the type of tools and analyses that will help your design. I want to talk about surface water and erosion control. So this is quite significant. It's the biggest Post-closure costs besides water treatment. It's also climate specific. This picture here is an example of some historic reclamation that was done at a mine site down very close to where I live in Tucson, Arizona. And you can see they decided that they would just cover the side slopes of the tailings with this cover material. They were able to get things to grow in it, but they never bothered to clean out the sediment that was occurring on the benches. And so what would happen is that the benches filled up with sediment, and then you get overtopping of surface water runoff. And so this cover system at the end of the day was just useless because they didn't consider surface water flow or erosion control in the design. And so it's quite important to consider the long term, and especially with surface water channels, you need to keep them clean. You need to keep the sediment out of them. Otherwise, the water will jump out and erode and destroy your cover. Now, just in general, on side slopes, it's important to have what we call erosion resistance. And so in this case, most semi-arid climates need some type of gravel in the side slope material to reduce the erosion. With temperate climates, you can use a mix of rock and vegetation. And then the main reason is that in arid systems, the vegetation is not thick enough to control the surface water flow and to reduce the flow rates. High precipitation climates, some high precipitation climates, you can get 100% vegetation cover, like in Papua. So if you can get that 100% vegetation cover, you've virtually eliminated or you've minimized the amount of erosion, because the raindrop impact is almost nothing at this point. This is an example of a site in Nevada where actually the channels were a little bit under design, and they jumped out of the surface water flow, jumped out of the channel, and then created a huge downcut. Okay, and so unless you design for this, you will be back out there fixing your channels. So in terms of the design, a principal consideration to maintain the integrity of the cover is the gully formation. And gully formation is progressive from downslope to upslope. It basically typically starts down lower, and then it continues to upcut and go up the slope. And this is due to the concentration. So water is starting to flow into these little gullies that form, and you get this concentration where water is feeding from different parts, and then it basically starts to downcut, and then it progressively unravels the cover as you go up. And this will cut through your cover, and it dramatically increases the soil loss rates. And this is due to a combination of possibly the cover materials not properly designed. There's not enough rock in it. There's insufficient vegetation. As your slope angle increases, you get higher gravity forces, longer slope lengths, overtopping of surface water conveyances. All of these need to be considered in the design. Now, erosion resistance, as I discussed, as the angle increases, the gravitational forces increase. In general, as the rock size increases, the erosion resistance increase. Widely graded rock is or what's called well-graded rock, where there's a lot of different particle size distribution. It's generally less resistance than where you have a more well-sorted type rock. Again, the type of rock, whether it's angular or subangular, and this gets into the design of what you put into channels. Riprap, for example, subangular rock is more stable than rounded rock. And then soil surface will self-armor. So if you have a material that has rock in it, the fines will wash out and you'll leave the rock on top. Now, I just wanted to show this graph here where you have, am I running over time?
10 more minutes.
Okay, I'll wrap things up here. And this is an example of where they went and they counted out the rills every 10 meters. And this was after a very large storm event. And then they compared it to the percent of bare ground. So basically, this is a relation to the vegetation cover. So the lower the value of bare ground, the higher the vegetation cover. And then as you get above about 45%, what they found is there was a significant increase in erosion. So in this case, the vegetation cover had a significant effect on the amount of erosion. And so you want to make sure that you get this level, or if you're not able to get enough vegetation, you need some level of rock armor on side slopes. Okay, just real briefly, you need to look at the design storm intensities. And typically these are between 5 minutes and 60-minute intervals. Okay, so the 24-hour storm doesn't really tell you what you need to know if you're designing for erosion resistance. And what's quite interesting is in the semi-arid areas, especially if you have convective type thunderstorm events, the design storm intensities can be quite high as compared to areas, for example, in the highlands of Peru or in Papua, where they get much more rain, but they don't get as large and intense storm events. So you need to be able to consider that. This is just an example of what I was talking about earlier, is that, theoretical flow going down a hill is straight, but actually what happens is you start getting a convergence of flow, and there's tools to use this. You want to make sure that you take a look at it. And this also will tell you, when is the slope too long, and where you might start causing problems for yourself. Some of the other side slopes challenges is how do you place geosynthetics on slopes? These are geocells, which are quite interesting technology solution where you can put topsoil into the geocells and it will stabilize the topsoil from eroding. And so this is in general, again, for more humid environments, but you need specialized equipment as well once you start getting above about 2.5 to 1. This is a tool called a slinger. And this is where you can actually, it's a high-speed conveyor. And so you can actually shoot material out over long distances. And this may be an alternative to spreading topsoil, for example, with a dozer. Okay, I'm going to switch off. Okay, so in kind of a conclusion on the design is you need to go and look at your trade-offs and considerations as we discussed with the cover system, its climate, your borrow sources, the ability to revegetate, the estimated net infiltration, and what is your CapEx, OpEx. For erosion, surface water control, those factors are side slope gradient, your side slope length, what's the vegetation, and also the amount of rock in the cover material. For example, a design standard we use for semi-arid areas is to have at least 50% of the material should be above a 1/2 inch rock. And we know that if you can get that kind of self-armoring, those slopes will be stable. And then there's a lot of considerations that you need to look at, which again are site-specific. And these are the types of questions that you need to be answering in the design process. And ultimately, it's important to keep in mind that some of these cover systems can be extremely expensive. And so the initial reaction is going to be, well, we can't do that. But if you consider that you may have to do water treatment, at that time you can do a proper evaluation, because if you're doing water treatment for 50 years, that can actually pay for a much more complicated cover system design. All right, so I'll just stop right now, and if there's any questions.
No, have you finished?
Well, I've got just a few more slides, but
Okay, go ahead.
Okay. So the last thing I wanted to talk about is long-term tests and monitoring. And it's important we can design all day long and we can run models all day long, but at the end of the day, this having some site-specific knowledge is most important, because at many mine sites you're talking closure costs that are in the hundreds of millions of dollars, and so making those types of decisions are it's much better if they're supported by actual on-site data. And so with long-term test and monitoring, we recommend that if you're going to do test plots or any type of study, that you monitor for at least 7 to 10 years. And this is in order to capture some of the variability that occurs in the climate. You can do test plots, you can do full-scale reclamation. The monitoring parameters you need to look at are climate, vegetation, soil moisture dynamics in the cover system, and then also be monitoring for erosion as well as landscape function. How is the vegetation developing? What is this going to look like 10 years down the road? And then the last thing that we recommend is at the end of your monitoring period, you actually go and you deconstruct the cover system and see if it has changed from the original design. So this is an example of some test plots that we have on a mine site in Peru. Fairly small, but they're wanting to look at what is the efficiency of a high fines clay layer unit. And so this is set up, and we have complete control on the water balance. We understand what's running off. We also understand what's coming out of the drainage layer. And so that's how we monitor. You need to monitor the water balance. If you have a site that's larger and you can't put in test plots, you can put in sensor nests. And this is basically a combination of water content sensors, what we call pressure potential sensors. This measures the energy of water. Is it going up or is it going down? There's also things that are called flux meters, and these are direct measurements of net percolation. So you'd say, well, if you have an existing reclaimed area, you can go in and you can actually monitor the performance by installing these sensor nests. And then when you decommission, just pull everything out and in situ testing of the hydraulic properties. This is actually a project we did at Pierina in Peru, and take a look at routing surveys as well. What was interesting at this site is that the roots went quite deep. The roots were almost 2 meters, and they went below the clay layer and actually into the heap leach material. And they were using the heap leach material to get water. So that actually improved the efficiency of the cover system. So in conclusion, I just want to say climate and biomaterial properties should guide the design. Use precipitation and PET ratios to guide your initial design evaluations. Use site-specific knowledge. You want to look at vegetation, rooting in natural areas. Often you can go to the side slopes and take a look at, well, how much rock is on the side slopes in the natural areas on the surface. And that tells you how much rock you need on the side slopes to control erosion. Looking at groundwater budgets as well will allow you to estimate what probably the natural recharge rates are. You need careful field investigations. This, like I said, we can discuss this in the workshop. And then use the models to evaluate relative performance. And this will help you, guide you. It's not going to give you a complete accurate answer, but it will guide you as to which cover systems are better than other cover systems. And then the last two things are you need to monitor your site, get an understanding specifically what's going on the site. And then we need to do more work on better understanding covers in tropical environments. We just don't have that much information yet. There's quite a bit coming out of Peru. There's the one mine property in Brazil that I talked about, but we need more information there. And that's it.
Okay, Mike. We have one question for you from Rafael Albuquerque, and it's the following. If you intend to use non-tag material, it might still not be literally inert. What kind of testing should you do? The regular characterization, static kinetic test of AMD studies, or there's something else?
Yeah, no, that's fair. That's a good approach. Yeah, I would start with the static tests, and if the static tests are within that range of 0 to 10 tons per of calcium carbonate per 1,000 tons of waste, you may want to use more of a simple cover then, and hedge your bets, basically. Ensure that the plants will get something to grow, and it could be 30 centimeters of topsoil. But then what you'll find is that the plants will use that 30 centimeters and for their primary nutrition and their water. But if the material is only slightly packed, then they can go and they can get water out of the waste as well. Okay. But again, it's
I have a quick question for you because we're running out of time. Is that a specific enforcement for tailings or waste biomaterial in US? And how is the legislation in US for this type of work service?
Yeah, it depends on the state. Okay, and so and every state's a little bit different, but for example, in the Southwest, in Arizona, Nevada, we've seen cover systems and we've worked on cover system designs that can be quite efficient, that will protect and put, be less than 2% of average annual precipitation. But it's also variable. So there is not a fixed standard, but in general, the goal is to reduce the amount of net infiltration to the maximum extent practicable.
Very good answer. Mike, thank you very much for your participation, and we hope you will be with us, and we hope to see you in Brazil in October for our Congress. Okay?
Yeah, that would be great.
Thank you very much again.
If you can pass on my email to the participants, if they have any questions, they can email me directly.
Okay, we can do that.
Perfect.
Thank you again.
Okay, thanks. I'll stop sharing.